Welcome to this lecture on materials of construction for corrosion resistance. My name is Dr. K. Ilaya Perumal. I am a corrosion and metallurgical consultant. In this lecture, we will talk about metallic materials only. There are non-metallic materials like plastics and Teflon which we will not cover in this lecture. The purpose of material selection is to choose materials for different equipments. Distillation column, condenser, reboiler. All the three will require different service conditions. For example, distillation column will not require heat transfer, whereas condenser and reboiler will require heat transfer. Distillation column will require strength. So accordingly, we should choose materials of construction. There are various stages in assuring corrosion resistance of a chemical process equipment. First is the material selection. The material selection should consider corrosion resistance, mechanical properties, and other properties like thermal conductivity. Once the material selection is done, the equipment should be designed. The main consideration in designing is a proper flow of liquid. There should not be any stagnation. The next stage is fabrication. During fabrication, right fitting and freedom from defects should be ensured. The next stage is welding. During welding, the weld metal and parent metal should match in composition. Otherwise, galvanic corrosion will result. Next stage is PWHT. That means post-weld heat treatment. The purpose of post-weld heat treatment is to ensure freedom from stresses which occur due to fabrication and welding. The next stage is NDT, non-destructive testing. The purpose of non-destructive testing is to ensure suitability for inspection. Inspection must be periodically carried out to assure corrosion extent. The next stage is special cases. There are special cases of equipments like pressure vessels, heat exchangers, reactors, etc. This will require very special requirements. For example, pressure vessels should be able to withstand very high stresses. Heat exchangers should be able to withstand thermal conductivity across the wall thickness. Similar considerations are applied for special cases. Information required for material selection. Material selection will consist of two stages. Service conditions, the chemical process service conditions to which the equipment will be exposed are required. These are the following: whether it is gas or liquid flowing, its chemical composition. The concentration of the corrosive species is also required. Then we should know whether it is static or dynamic condition. Static means storage vessels. Dynamic means either pump or liquid flowing in pipe. Then temperature, pressure and flow velocity during design stage and also extremes are required because temperature, pressure and flow velocity affect the corrosion rates. Then, in addition to these service conditions, which are based on chemical process, there are conditions which are based on equipment details, like whether it is static equipment, like tanks, columns, reactors, flanges, fittings, or dynamic equipment like pipes, heat exchanger, tubes, pumps, and valves. So all these considerations are required before the proper material selection is made. There are additional considerations in material selection. There are two aspects of material selection. One is initial cost and the other one is operating cost. These two are to be considered for the final material selection. The initial cost consists of selection of a material based on mechanical properties, corrosion resistance, fabrication cost, and immediate material availability. All these four factors will determine the initial cost. In addition, there is an operating cost. The operating cost are consisting of four contributions: the material availability as and when required, the fabrication costs to make the spare parts, production losses due to the necessity of changing the parts, maintenance costs, which are additional fabrication cost. So these two factors, initial cost and operational cost, will decide the total design life cycle cost. Ultimately, for the end of the plant life, this cost is more important. So the aim in material selection is to minimize the total life cycle cost and not aiming only at the initial cost. The operating cost and the initial cost should be added together to arrive at total design life cycle cost, and that should be aimed at the minimum value. I'm going to show you a spectrum of various materials of construction. We will start with plain carbon steel. For most of the purposes, because plain carbon steel is the cheapest one and its technology is very well known, people use plain carbon steel. This is very good with respect to manufacturing and availability, but unfortunately this is highly corroding. The corrosion resistance can be incorporated by giving a paint coating. The paint coating will survive most of the corrosion situation except the following conditions. For very high corrosion resistance, improved corrosion resistance, if that is a requirement, then we should go for stainless steels. In addition, if the improved heat transfer is the main condition, like heat exchangers, refrigeration coils, heaters, etc., then we should go for heat conductive materials like copper-based alloys. Copper, brass, etc. are more conductive than carbon steel and also stainless steel. These materials also have certain corrosion problems. Stainless steels are susceptible to chloride pitting and stress corrosion cracking, whereas copper-based alloys are susceptible to ammonia corrosion and stress corrosion cracking by ammonia. To overcome These problems, the practice for several years is to go for better material of construction, which is normally nickel molybdenum alloys like Hastelloy C276 or nickel chromium alloys like Inconel and Incolloy. The basis of selection of nickel-based alloys are shown in the next slide. Here you can see the effect of nickel content on the corrosion rate of steel. The more and more you add nickel, the corrosion rate comes down. So this shows the standard materials like 304 stainless steel, 316 stainless steel, nickel-based and nickel-based alloys. This figure corresponds to sulfuric acid, but this is applicable to most of the environments. So using this, the next class of materials have been developed. Nickel molybdenum alloys and nickel chromium alloys, they also corrode under very heavy corrosion conditions. In those cases, very expensive materials like titanium, tantalum and zirconium are used. Titanium is very well known in chemical process industry for seawater applications. Tantalum is the ultimate corrosion resistance. Zirconium is used in special considerations like urea and nuclear plant, etc. In this spectrum, when you go from bottom to top, corrosion resistance increases. So it is obviously very clear when you go from plain carbon steel is the most corroding material to all the way to tantalum is very highly corrosion resistant materials. Unfortunately, the initial cost is also increasing very heavily. Assuming the cost of plain carbon steel is X, stainless steel will cost 30X and nickel-based alloys will cost 300X. So that much increase in initial cost. To reduce this cost, a lot of research went on and they produced in-between materials. These materials are called super austenitic stainless steels. You can see the difference. The normal stainless steels are called austenitic stainless steels, whereas this is called super austenitic stainless steel by increasing the nickel content. The common super austenitic stainless steel is alloy 20, 904L, etc. These are used for highly corrosion resistant applications. Further research were carried out to reduce this cost also, because super austenitic stainless steel contain very high quantity of nickel, and nickel is an expensive alloying element. To reduce this, more and more research was carried out to reduce this gap. The background of developing duplex stainless steel is shown in the next slide. This figure shows the background of developing duplex stainless steel tubes. What you are seeing is the resistance to stress corrosion cracking as a function of nickel content. And you will notice here just about 10% nickel, the resistance to stress corrosion cracking is the lowest. So when you reduce the nickel, the resistance to stress corrosion cracking increases. On the other hand, when you increase the nickel, again stress corrosion cracking resistance increases. But increases the nickel means very expensive. Reduces the nickel means less expensive. This is the background of duplex stainless steel. These are the common duplex stainless steel tube stainless steels available and presently used for various applications. One can notice that nickel content is very low compared to normal austenitic stainless steels. That is why it has become cost effective, and the chromium content is higher than the normal stainless steel. That is why it has become corrosion resistant. So all plus some molybdenum and also some nitrogen are added to the duplex stainless steel. These elements will make duplex stainless steel as a mixture of two phases. That is why it is called duplex. Duplex stainless steel is normally termed as a tale of two faces, something similar to saying a tale of two cities. This duplex stainless steel will have a two phases austenitic phase, which will have good corrosion resistance but poor resistant to stress corrosion cracking, SCC. But it has got good formability, weldability and toughness. On the other hand, duplex stainless steel will also have ferritic stainless steel, which will have a very good resistance to stress corrosion cracking but difficult to weld. So when you mix both of these around 50-50, you get combination of properties. You can see the typical microstructure of duplex stainless steel, partly austenite and partly ferrite. If any cracks develops due to austenitic structure, the ferritic structure will stop. That is the reason why duplex stainless steel has got ultimate corrosion resistance. Duplex stainless steel is a combination of both the above phases, austenite and ferrite. Almost 50% austenite and 50% ferrite. Superior resistance to stress corrosion cracking because of the ferrite, and good yield strength, formability and weldability because of austenite. So that is the reason duplex stainless steel has come to stay, and it is a popular grade for most of the applications. Duplex stainless steel, in addition to corrosion resistance, it has got attractive tensile properties. You can notice here 316L is a common austenitic stainless steel. As compared to that, the duplex stainless steel and also super duplex stainless steel, they have a very high yield strength, very high ultimate tensile strength with reasonable good ductility. All these properties make duplex stainless steel amenable for fabrication and maintain good strength. So in this lecture we have seen material selection spectrum. Different informations are required for material selection for a chemical process equipment like corrosion resistance, mechanical properties, cost, etc. The materials covered in this lecture vary from plain carbon steels to duplex stainless steel having satisfactory properties. Thank you very much for this short lecture on material selection. This book you see here is written by Professor V.S. Raja and myself, Professor V.S. Raja from IIT Mumbai. You can get many details about material selection in this book. This book has been published by John Wiley, USA, and is available online through Amazon. Thank you again.